We've talked a little bit about multiple linear regression. And I say a little bit because you really could take an entire course on linear regression. One thing you might learn in that course is that regression, the analysis, the process, it involves a lot of steps, and you have to be very careful. It's a powerful tool, and with great power comes great responsibility. Some people have structured this idea that there are lots of different steps in the regression process. It starts with, how do we design the study? What is the research question that we're interested in? Where do our data come from? How do we select these variables? How do we look at these data? How do we visualize them? I want to take a couple of these steps and explore them in a little more detail. Again, just to whet your appetite. This is an introduction to the 14 steps of regression analysis. Let's talk a little bit about the assumptions and then the assessment of the model. Any statistical test is going to have assumptions. These are some sort of checkpoints or guidelines or criteria that we need to make sure are in place so that the test works. We've seen some of these before. The data points need to be independent of each other. For a linear regression, we need to have data that a line makes sense, right? Does it make sense to draw a line through these data? As far as the data themselves, we need to make sure that things are relatively normally distributed in the population, so that the mean, when we predict the mean of some outcome, so that it makes sense. We're also going to introduce this concept of homoscedasticity, where we look at the variance at each level of X when we consider predicting the Y. I love this slide. A lot of people don't like it, but we really want to think about this outcome variable, whatever it is, this dependent variable, has to be normally distributed at each level of X. You can tilt your head all the way to the right and see, if I'm talking about, say, this range of X's, do I have a roughly normal distribution of the Y variables? And the way we look at this is we look at the residuals. How far is each point from the line? And then we examine those residuals, some sort of residual analysis. We look to see, again, at sort of each level of X, how much variability is there in Y? Is it roughly the same? How are those points spread out at these different levels of X? Here's a normal distribution of this variable, normal distribution of this variable. This is nice. This is known as homoscedasticity. Homo means the same. Skedasticity is a Greek word for scattering or dispersion or spread out. Here we see heteroskedasticity. This is classically described as fan-shaped. I think it's fan, like to fan your face. I've had students say it looks like a Dorito. The variability at this level of X is much more than the variability at this level of X. It might be a sign we need to do a transformation to meet this assumption. One of the transformations that we've seen commonly used is log transformation. These are really cool data on the relationship of an animal's brain to its body weight. And if I just plot out all these points, you can't really see anything because the scale is a little bit off. But when I do that log transformation, take a look at this relationship. This is awesome. I'll draw lines through this all day. So we talked a little bit about model assumptions. Let's talk a little bit about model assessment. We've talked about things like the R squared. We've talked about the F test. You'll learn how to do diagnostics on your residuals to see how well the model fits. I want to talk a little bit about some of these tools that can be used to look at influential points in your model. The residual plot ideally will show us just some random sort of cloud. If you look at each point and its distance to the model, that's the residual. And we can plot out those residuals relative to the estimate and see that, hey, there's just a cloud. There's no pattern here. Sometimes we might need to look at influential points, outliers. The gut is to throw outliers away, but we want to explore them. From anomaly commences discovery, we've said. If you have an outlier in the Y variable, it's some model failure. This person, I'm trying to make a prediction for them, but the prediction doesn't work. It's too high or it's too low. We might have some sort of outlier in X. Technically, this would be some sort of leverage point. If you have an let's say you're looking at how the size of a car affects its fuel economy. If you have only one SUV, only one giant truck in your database, it could have a real influence on what the model looks like. It could affect the slope. Let me draw what that would look like here. Let's say I have a bunch of points here, and I draw a line through them. And then suddenly I get one point which has a very large X. What will that Y value be for that X? Well, if it's low, what will happen to that slope? That slope would come down. If it's high, what would happen to that slope? That slope would go up. So this point actually has the potential to have a lot of influence on the model. There's a guy named Cook who came up with an interesting idea on how to quantify the effect that that a point has on the model. He came up with this idea of Cook's distance. And what he said to do is, hey, take out a point, refit the model, and see how the predictions of the other points change. It's kind of a cool idea. Hey, take it a step further. Do this for every single point and look to see how a given point influences the model of a whole. We don't want to make a model that's just based on the influence of one or two points. And you see a rule of thumb for what is a high value for Cook's distance. There's another number which is called the DF beta. And the DF beta measures how much does each point affect all the other slopes. Take the model, fit it, take that point out, fit the model again, and see how much the slopes change based on that point. So you get a number for each point on each slope. Again, the details here aren't important, but I want you to get a flavor or a taste of some of the important, post-analysis steps that need to be done in order to assess your multiple regression. Now, why do we do this? I like this quote. We're usually happier about asserting a relationship if it's appropriate after we randomly throw out a few people. We are happier if the relationship permeates all the observations and does not derive largely from one or two. What is the best model here? If you have a regression analysis, sometimes you find yourself with a lot of different predictors, and there are dozens and dozens of models that you can make. And you have to decide, what is the best model here? What is the best model? And partly, I think it was Voltaire who said, hey, if you want to argue with me, first define your terms. What do you mean by best? And we often find that best is a trade-off between how accurately does this predict and how simple is the model. And we'll have to try to decide what is our ultimate goal here with the analysis. This sometimes is a harder question to answer than you might think. You might say, seriously, what's the best model? Just tell me. The answer, of course, it's a good question. The answer to every good question is it depends or it doesn't matter. In this case, it depends. Are we asking about a given predictor and how it's related causally to the outcome? Or we're trying to say what best predicts the outcome? I can throw anything into the model that I want. Jerry DeLaw has a really good reading. It's called The Most Important Lesson You'll Ever Learn About Multiple Linear Regression. And if that's not enough clickbait for you to go and see what that lesson is, well, that's up to you to decide. Now, it's worth me mentioning that every statistical program has built-in tools to help you choose the best model. I don't like them. I think they're too often an easy way out and a substitute for common sense and hard work. And the common sense, the hard work, thinking carefully about how to specify the model, that stuff is much more useful than just clicking a couple buttons and doing one of these stepwise regression methods.